Kinematics Equation 1. Sometimes during an object's motion, its velocity will change. For instance, if you're driving to the grocery store, there may be a highway where the car travels quickly, and there may be stop signs where the car's velocity is 0. The average velocity for the trip can be found by dividing the total displacement by the elapsed time. The symbol for average velocity is v with a bar over it. The average velocity can be positive, negative, or 0, depending on the motion with respect to the starting point. The average velocity can't tell us the velocity at every moment in time. It's just the average for the entire trip. Continuing with our trip to the grocery store. When the car stops at a stop sign, we say that its instantaneous velocity is 0. The instantaneous velocity is the velocity of an object at a very brief moment in time. Mathematically, v instantaneously is delta x over delta t as delta t gets very, very, very close to 0. And that's the first hint of calculus. That's what Newton worked on, basically to solve physics problems. Your instantaneous velocity can also be positive, negative, or 0, depending on the motion. Acceleration is the rate of change of velocity. So that's delta v over delta t. And we frequently represent that as v, final velocity, minus the initial velocity, divided by the elapsed time. A lot of times we just say that the initial time is 0. So in words, acceleration is change in velocity over elapsed time. Acceleration is a vector. It has magnitude and direction. Although in one-dimensional motion, which we're doing, we only need the sign, right? Plus in that direction, minus in the opposite direction. Since only constant acceleration will be considered in this course, in other words, acceleration that does not change, there's no need to differentiate between average and instantaneous acceleration. They're the same. You can derive the units by substituting the correct units into the right-hand side of these equations. So acceleration, delta v over delta t. Velocity is meters per second. Time is second. So that works out to be meters per second squared. Let's derive Kinematics Equation 1, and we're going to start with the definition of acceleration. Delta v means change, so delta v is v minus v0. Delta t is t minus t0, and we're going to let t0 equal 0. We'll start the clock then. Therefore, delta t will just be t. So we have a now is v minus v0 over t. Then we're going to solve for v, the final velocity, multiply both sides by t, clears the t on the right side. Then just reverse the equation, left to right, right to left, and we have v minus v0 equals at. Add v0 to both sides, and we have the final velocity is the initial velocity plus acceleration times time. So that tells us how an object's velocity changes as a function of time. And again, this is Kinematics Equation 1. Example 1. If an object accelerates from rest with a constant acceleration of 5.4 meters per second squared, what will its velocity be after 28 seconds? We write down our givens, and here's a code word. From rest means your initial velocity is 0 meters per second. Your acceleration, 5.4 meters per second squared, and the elapsed time is here. So, Kinematics Equation 1, we don't have to do any rearrangement at all. We put in the givens. v0 is 0. Here's our acceleration. Notice we put the units in, so you can see that this second will cancel out here, giving you meters per second, which is nice. And then we get 151 meters per second. And make sure you box your answer or underline it or put an oval around it, anything to help your teacher grade it. Example 2. An object is traveling at a constant velocity of 15 meters per second when it experiences a constant acceleration of 3.5 meters per second squared for 11 seconds. What will its velocity be after that acceleration? We start, as always, hopefully, by writing out our givens, and this time we are not starting from rest. We have an initial velocity. So we have our Kinematics Equation 1, and we'll need to plug the v0 right into there, 15 meters per second, plus acceleration times time. We've substituted in the givens, do the math, and we get 53.5 meters per second. An object is moving at a velocity of 23 meters per second. It then accelerates to a velocity of 85 meters per second over a time of 8.3 seconds. What acceleration did it experience? We write out our givens, initial velocity, v, and time, and we need to find acceleration. So we have Kinematics Equation 1, but the problem is we need to solve for acceleration. Do not plug the givens in yet. Solve for acceleration first. So first of all, we get v0 on the other side by subtracting it from both sides. So we have v minus v0 equals at. Then divide through by t to isolate a, and then another step, just switch it around. So you have a on the left side instead of the right, and you have v minus v0 over t. Now we can substitute in our givens. Here's the final velocity, here's the initial, here's the time, carry out the math, and we get 7.5 meters per second squared. A car is driving at a velocity of 24 meters per second. If its brakes can supply an acceleration of -5 meters per second squared, how much time will be required to bring the car to a stop? Very important, the negative sign. So if you're moving in this direction and you have a negative acceleration, what's that going to do? That's going to slow you down, which is good because that's what we're asking. We want to bring you to a stop. We write the givens and be very careful to include that negative with the acceleration. So we have the Kinematics Equation 1. We're looking to solve for time. So we start by subtracting v0 from both sides, then divide both sides by acceleration and reverse the equation. So we have t on the left. We get t as v minus v0 over a. Now we substitute in the givens. Our final velocity, again, that was a code here. Bring the car to a stop. They never said your final velocity was 0, but when you're stopped, your final velocity is 0 meters per second. So we have 0 meters per second minus 24 meters per second over -5 meters per second squared. So what's nice on that is you have a negative in the denominator and negative in the numerator, so that will cancel out and you'll get a positive time, which is very good. So you have time 4.8 seconds.